Welcome back, guys, to Remote Explorations. I am Sinjan, currently a first undergrad at IMA Bhubaneswar, trying to build up a career in mathematics. Welcome to my channel who are new here. I have started the lecture series for the upcoming ISI CMI entrance examinations, which is scheduled for 11th May and 24th May respectively. So our first chapter, polynomials, it consisted of 4 lectures. We have successfully done it. Now we are going with number theory. So in my last lecture, I had completed up to your Sophie-Germain identity, which is a nice way of factorizing composite numbers or proving composite numbers. That is a nice way of factorizing. So now today's main agenda would be to understand congruences. Agenda for today. Number one is fundamental theorem of arithmetic. Next is your fundamental theorem of arithmetic only has corollary part holding the number of positive years of a composite number. Then we will be moving forward with one or two questions, and then I will be coming with your congruences, which is the main area of focus in number theory. So without any further delay, let's get started to it. Today is also going to be an approximately 1 hour video. Let's get down to it. So yeah, what is our fundamental theorem of arithmetic? What is this thing? This basically says that every integer greater than 1 can be denoted as a product of primes. This is the main statement of some sort of glitch. Yeah, sorry for this. Is happening, guys. So I can't figure out the problem right now. So just ignore this thing. What does my fundamental theorem of arithmetic say? Every integer z greater than 1 can be denoted or written as a product of primes. So basically, if I want to recreate this, this will be n is equals to p1 to the power alpha 1 into p2 to the power alpha 2 into p3 to the power alpha 3 into dot 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 into p to the power m, pm, sorry, l to the power alpha m, where my p1, p2, p3, all the way till pm are distinct primes. P1, P2, dot dot dot. After PM, they are my distinct primes. So unfortunately, my current has gone, but that's not an issue. And my alpha 1, alpha 2, all the way till alpha m, they are my natural numbers. So they are my natural numbers. So this is basically this thing. So my n is a number which is greater than 1 and it can be expressed as a product of primes, and the primes can be raised to any number of powers. Now from here we come to one corollary. One extra case, I should say, or probably special case. Extra special case. Which is your number of positive divisors of a composite number. Number of positive divisors of a composite number. So now, if my number is n, it is a composite number and it can be expressed in the form of p1 to the power alpha 1 into p2 to the power alpha 2 dot 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 all the way till pn to the power alpha n. Then the number of positive divisors. Then my number of positive divisors of n is basically your, it is denoted by tau of n. Okay, so tau of n, my tau is a symbol, it's the Greek symbol which represents t of the English alphabet. So my tau of n is basically represents the number of positive divisors of n, which is equal to my here, if I go, my tau of n is equals to alpha 1 plus 1 alpha 2 plus 1 into alpha 3 plus 1. Sorry guys, you might find a bit disruption in the video since it is lagging. Dot, dot, all the way till alpha n plus 1. So this is what my tau is. For example, so we will be trying to take a small example and we'll be seeing that my results hold valid or not. So example, let my n be 24. So if I want to my factorize my 24, so factorize my 24, It could be going with 2, so that gives me 12. So this is my 12. This is my 2, it gives me 6. So 2, it gives me 3. So my 24 in the product of primes can be written very easily as 2 cube into 3. That is basically your 8 into 3. So ultimately this is your 2 to the power 3 into 3 to the power 1. So this is my P1, this is my P2, this is my alpha 1, this is my alpha 2. Therefore, if I want to calculate my tau of 24, that is the number of factors of 24, I have to do basically a 3 plus 1 into 4 plus 1. That means this is not 4 plus 1, this will be over 1 plus 1. Sorry. So 3 plus 1 is 4 into 2, that is my 8. Now time to check that is whether it is correct or not. So I will be listing out my factors of 24. It would be including both primes and composites. So 1, 2, 3, 4, 6, 8, 12 and 24. How many do we have? So this is my 4 and this is my 4. So 4, 4, 8. My results are matching. Yep. Hence this is my correct answer. Now, one more specific case. What is the case? Special case, you could say. My special case, I should be writing it in red, I guess. If n is a perfect square, that means basically my alpha 1 comma alpha 2 all the way till alpha n, they all are basically your even numbers. It has to be even numbers. That means my alpha 1 plus 1 sorry, alpha 2 plus 1, all of them would be odd numbers, which ultimately suggests that my tau of n, which is basically my product of alpha 1 plus 1 into alpha 2 plus 1 all the way till alpha n plus 1, is basically a product of odd numbers. So ultimately that suggests that if my n is a perfect square, then my tau of n, that is my all number of factors of n, has to be a odd number. This is what my results suggest. Now one more special case. What is my one more special case? Piece is getting overheated, so it's becoming a problem. But I have found a solution though. Okay, so my another special case is basically here. Till now we are find out the number of divisors of a composite number. Now we are gonna have to remember to memorize one more formula which suggests us the number of ways of finding out the positive divisors of a composite number. The water. It's too hot in Bhubaneswar out here. Number of positive divisors. It is basically denoted by sigma n. I will be changing my color to red. So my normal number of divisors denoted by tau of n, and this is divided by sigma of n. This is ultimately gonna be 1 to the power of alpha 1 plus 1 minus 1 by p1 minus 1 plus p2 to the power of alpha 2 plus 1 minus 1 by p2 minus 1, and this is not plus. Okay, so this is my multiplication. This is into p3 to the power of alpha 3 plus 1 minus 1 by p3 minus 1, and this goes on and on all the way till pn. So this is my formula for finding out the number of positive divisors. Cool. Just take over 2 to 3 minutes to digest it while I found out if there's any problems, or else I'll be shifted into the main area of focus, which is my congruences. I hope all of you have seen it. So most probably I don't have any problems. Yeah, let's come to modular arithmetic, which is mine. Congruences. Next thing in our to-do list is your congruences. Okay, so I'll be starting with green. It's my favorite color. So my statement in congruences basically your A congruent to B mod N. This is basically the full chapter congruence deals with. Now, this is my congruence sign, congruence modulo. This is my congruence modulo sign. So now what does this mean? This basically means my N completely divides A minus B. Or my A is equals to Kn plus B for some K belonging to real. So here if you look at it properly, then this is basically denotes the division algorithm in a much better way. How? So I have my A is congruent to B. So if we look at it, my this A is up here, so this becomes my dividend. I'm dividing it with N, so N becomes my divisor. And I am left with B, so here B becomes my remainder. So this is your A is equals to Kn plus B, where my dividend is A, N is my divisor, and B is my quotient, or sorry, B is my remainder and K is my quotient. So basically, dividend is equals to divisor into quotient plus remainder. Ultimately, my congruence denotes the normal basic Euclid's division algorithm. 2 minutes to digest it. Easy one, not much tough. Good. We have some properties related to modulus. Now we come to properties. My PC is hanging, guys. So do bear with my screen freezing and all. I am there, all waiting for you to just complete things up. Next comes up is your properties. I will be just checking up my charge once. Sorry to disturb you guys. Okay, so I think I need to put my device on charge. So next comes up my properties. This is my property number one. What does it say? A, even if you don't understand congruence, just try to understand congruence in the form of division algorithm and it will be super easy for you. So my A is congruent to A modulo n. First property. My second property is here. A is congruent to, if my A is congruent to B modulo n, then my B is congruent to A modulo n. This is my symmetric relation. This is my reflexive relation. This is my symmetric relation. Now we also have my transitive relation, which is your if A is congruent to B mod n, and my B is congruent to C mod n, then ultimately it will be giving me that my A is congruent to C mod n. This is my transitive relation. My transitive relation. Now some more properties. So if my A is congruent to B mod n and also my C is congruent to D mod n, then we have some recurrence properties, that is some properties based on only these two statements. Number one is A plus C is congruent to B plus D mod n. A minus C is congruent to B minus D mod n. AC is congruent to BD mod n. AX plus CY is congruent to BX plus DY mod n for XY belongs to integers. For X comma Y belonging to integers. This is my one set of recurrence or recursive properties. You see it once, then we'll go into my next set of properties. I guess you all are done seeing this. So my next set of properties is if my A is congruent to B mod n, then A plus C is congruent to B plus C mod n. Again, the electricity has gone. My A minus C is congruent to B minus C mod n. AC is congruent to BC modern for any C belonging to your real number, okay? Some huge problem with electricity in this area. My A to the power M is congruent to B to the power M modern. Now, one interesting property which will be helping us in polynomials too is basically this one. If my, sorry, if my A is congruent to B modern, then my A to the power M is congruent to B to the power M modern. Nope, nope, nope. Extremely sorry, guys. That means my f of A is congruent to f of B modern, where my f is a polynomial over Z, is a polynomial over Z, with one important condition is with integral second buffering, guys. If where my f is a polynomial over Z with integral coefficients. These are some of the basic properties. Now, time to do a little bit of questions, I guess. Let's see. Some good question. The question I need the recommended book. It's your test of mathematics at 10 plus 2 level of the tomato. Let's see. There must be MCQs. You know, like, let me give a suggestion. Right now, I am doing chapters. That's okay for your revision. But most probably, don't just believe in my chapters. Since right now I have started teaching, but that doesn't mean I'll be able to complete everything with total details in before 11th of May or before 24th of May. So basically, guys who are preparing for ISI and CMI, don't blindly follow this as your normal course. This can be your crash course. This can be your very, very, very good crash course. Since all the things I'm doing in very concise way and in super accuracy and super precision, but not in that detail. Like the proof behind each problem or the proof behind each result. Like if I go up here like this, so this all things they are single proofs. So if I tell you to prove this, you need half a page to actually prove it. So I'm not going the depth with that. I'll be going once this ISI is over, then I will be designing a proper curriculum keeping in mind the next year's ISI, CMI, and IMA and other mathematical entrances examinations. So this is basically not your course. This is your crash course. And problem practice right now, you basically have two jobs, two duties as a student. Number one is to see my crash course and revise from your notes, and number two is to practice whole lots of questions and probably try to complete this tomato. This is what has to be a target right now. Okay, so right now I am getting any question which I'm getting one very easy question. So it is basically given the number of different factors of 1800. You need to form that same formula, use that same formula. Like I'm just doing this for you. This is an easy one. Just showing you the real life application of the problem. So my question is number of divisors or probably number of different factors. So basically it is number of divisors, number of different factors of 1800. So you need to first factorize 1800. So 2 it is my 900, dividing by 2 it is my 450, dividing by 2 it is my 225, dividing by 3 it is my 75, dividing by 3 it is my 25, and 25 is basically 5 into 5. So dividing by 5 is 5 and dividing by 5 is 1. So if I want to write my 1800, this can very easily be written as 2 cube into 3 square into 5 square. Hence, my tau of n, which denotes the number of factors of n, is basically 3 plus 1 into 2 plus 1 into 2 plus 1. So ultimately, this is my 4 into 3 into 3, which is my 36. So 36 factors is the answer. Whew. The number of different factors of 1800 we are done. You have actually 5 to 6 questions here which is on number of divisors finding out, so you can very well try them. Then we have our Fermat's theorem, which is what I'm going to teach you right now before we move on to complete residual system modulo n. But before that, I will be liking to do some important functions of theorem. Which will be very much helpful while we are going for CRT, which is the Chinese remainder theorem, or my Wilson's theorem. So this is my basically your, probably I will be writing the heading first. some important theorems. First thing I'm drinking some water. You guys also should hydrate yourself. Give me 2 minutes. Yeah. So Euler's totient function is my first important theorem. Euler's totient function. Totient. If you want, I'm gonna attach, not you want, I am really gonna attach by today only or probably by tomorrow, the notes of my teacher while I was preparing for ISI and CMI. That is Mr. Hardik Kalra, who is currently in CMI doing his masters. I will be attaching his notes in my blog site under a separate section to uh, help you guys understand it better. But for that, you guys really need to subscribe to my blog and follow my blog and love it and share it with more people, just like you're doing with my channel. So I really want you guys to read my blog. So what is my Euler's totient function? So Euler's totient function is denoted by my phi. Okay, so my phi of n is basically your number of positive integers. My phi of n is basically your number of positive integers less than n, or less than, or I should write, or equal to n, and relatively prime to n. or co-prime with n, prime to n, or co-prime, which is prime with respect to another number, co-prime to n. This is my Euler quotient function. It is a multiplicative function, hence very easily if my phi of mn is equals to basically phi of m, so my phi of mn is equals to phi of n into my phi of n. This is an important result. One more property, this is a general one. Another property is my phi of p is p minus 1, where p is my prime, where p is a prime. For example, 3. Now if you go for 3, so phi of 3 is basically finding out the number of positive integers lesser than or equal to 3 and relatively prime to 3. So number of positive integers lesser than or equal to is basically 1, 2 and 3. Relatively prime to 3 is 1 is prime relatively prime to 3 and 2 is prime to 3, but 3 is not prime to 3. This is both, they both have common factors including 1 and 3. Just a second. Okay, so yeah, hello. Yep, good. Now my phi of p is p minus 1. Next one is simple one. My phi of 1 has to be 1. This is very easy. Now, one more thing is my I need to see this result and tell you guys it's a big result. We don't usually remember it, but just try to remember. Which is your if my n is of that form where we had to find out the number of divisors of a composite number. If that is if my n is basically p1 to the power alpha 1 into p to the power alpha 2 into dot 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 up till pn to the power alpha n, then or probably this, let this be k, okay, then my phi of k, that is my number of integers lesser than or equal to can co-prime to k, is basically 1 minus 1 by p1 into 1 minus 1 by p2 dot dot up till 1 minus 1 by pn. So this is what is basically finding out number of factors for number of numbers lesser than or equal to co-prime to n, where n is my composite or a prime which can be written as a product of two prime or more than two primes. Now Carmichael's theorem, I'm going to skip Carmichael's theorem for now since it is not of that much importance in ISI and CMI entrances. Now we'll be going to Fermat's theorem. So what does my Fermat's theorem see? this Fermat's theorem is probably going to be my last topic for the day. After this, we won't be taking, let me just tell you what we are going to do. After this, I won't be taking a complete lecture of number theory. My next lecture, which will be coming probably day after tomorrow or the day after that, it will be consisting of my Euler's theorem and my Wilson's theorem and my Chinese remainder theorem and 3 to 4 problems regarding that, which I will be doing from my tomato, that is test of mathematics at 10+2 level. And my next video half would be of number 3 and my next half would be of the chapter I would be starting next, which is your permutation and combination. Most probably it is gonna be permutation combination, or if not, then probably I'm gonna start up with your binomial theorem and recursions. But yes, as far as I want, my wishes are I am gonna start, or probably I can also go for sequences and series. Most probably it will be permutation combination or APGP HP. So if you guys are watching this properly with all your notes and all, so do comment what you want next, which one is your week one. I will be going with that, but most probably it is going to be sequences and series, since if many questions are then permutation combination which needs the knowledge of sequences and series. So today's last one is basically your Fermat's little theorem, or simply Fermat's theorem. Let's take a 2 minutes break. Yeah. So my Fermat's theorem. What does my Fermat's theorem say? It basically says that I'll be changing the color for any prime P and any A belonging to integer, my A to the power P is congruent to A mod P. That means my A to the power P minus A is divisible divisible by p. So this is what Fermat says. For any prime can be integer a to the power p is congruent to a mod p. What's Fermat theorem say you? So I'm just gonna bracket it out for your better understanding. So this is what my Fermat's theorem is. Also, guys, what have we done today? We started with your fundamental theorem of arithmetic. I told you every integer can be written or denoted as a product of primes. Sorry for the pronunciation. Number of divisors of composite number, that is my special case, which is your alpha 1 plus alpha 1 into alpha 2 plus 1 into alpha 3 plus 1 up till all the way to alpha n plus 1. Showed you an example. Special case for n is equals to prime. My tau of n, that is my number of factors or number of divisors of n, has to be an odd number. Another special case is the number of positive divisors. So the first one was only the number of divisors. The second one is going to be the number of positive divisors of a composite number. So that is basically going to be p1 to the power alpha 1 plus 1 minus 1 p1 minus 1. If my number can be written in the form p to the power alpha 1 into the power alpha 3 dot dot dot. Congruences scheme. It's again hanging. Right now it's cool. Okay. So congruence is A congruent to B mod n. So dividend divisor remainder, just make it analogous to your congruences. So I showed you some properties whose proofs, if you want, you can give it a try in your own copy. It's very easy. Normal nominal proofs, right? Try to write in the form of division theorem and solve. It will be very, very easier. And the actual proofs are also done in that way. Number of different factors of 1800. I showed you an example. Then came my some important theorems. Euler's totient function, that is number of positive integers lesser than or equal to n relatively prime to or co-prime with n, that's a phi of mn. So then we came down to Fermat's theorem, which says that for any prime p and for any a belonging to integer a to the power p is congruent to a mod p. So that's it for today, guys. I hope you all liked and enjoyed the video. A little bit of buffering and the screen was hanging, so I'm sorry for that. I'm gonna try to rectify it from my next video. So that's all for today. Have a great day and try to ace the exams. Do like, share, and subscribe the channel and also my blog site. I'm gonna upload it in my description box today. So that's all for today. Goodbye, guys. See you soon. Love you.